This is Duke University.
How do we support their creation of a consensus on what they want to achieve? And how do we extend data management systems beyond data management to management of information and knowledge, which then poses the question, what types of information and knowledge do you actually have to manage? And how do you do all of this in a computer actionable form? We want the computer to do all the work. The users get to tell the computer what they want to have done, and the computer has to respond. So the communities that use this are distributed around the world. This is production software. There are communities that manage petabytes of data, thousands of terabytes. There are communities that manage hundreds of millions of files, hundreds of millions of attributes about the data, where the collection itself can be distributed across continents around the world, and it can be accessed by each community's preferred client for interacting. So a web browser or a digital library or a workflow or IO library. NASA requested a Fortran IO library interface, so there's one of those, etc. There are, in effect, three major categories of types of applications we see out there. There are groups that just want to facilitate sharing of data, management of data that they're creating in one place, they want to store in another, they want to access from a third. This National Optical Astronomy Observatory is a nice case. They have telescopes in Cerro Tololo, Chile, and all their researchers are in the US. So they've got to move the images taken by the telescope every night to an archive in the US, publish them so that other astronomers can gain access and manage that process. And they run it completely automated. So the system should be doing this for them without any manual intervention. Another category would be digital libraries. So the French National Library builds on top of this technology. They just did a migration from an obsolete storage environment to a new storage environment. And because they're using the data grid to manage the data, they could do it completely transparently to the user. So this facilitated their management of data as they tried to maintain contact with the most recent, least costly technology. And then there are groups that really build archives. So the NOAA's National Climatic Data Center manages various projects that are actually building on the technology. Each of these communities has a different driving purpose. They have a different type of data they're trying to manage. They have different requirements for access or distribution, retention, disposition, different standards for semantics. So if we look down here, a nice one is the cosmic ray experiment on the International Space Station. They're actually taking the data, putting it in a data grid so they can then share it with other researchers on that project. Control access while enabling some particular people to manipulate the data. Part of the community consensus. Who is our representative community that we're interacting with? Is it just the people who are creating the data, or is it also a specific user community? You can think of this collection that's being assembled as the set of data, information, and knowledge I want to make available, and I, as the creator, are going to make some assertions about it. These are its properties. I, as a user of that data, have my own requirements. So I need to be able to map from what I need to whether or not they're capable of providing it. So all of these groups have to think about their user communities, and are they providing the right properties so the users will be happy. With a computer actionable way to enforce a consensus. And the approach we've taken is to define a consensus as a set of policies that can be automatically enforced within the data management environment. So I could have a policy which is expressed as a computer actionable rule, is stored in a rule base. I have a policy then which can enforce a management decision where the data should be distributed, a policy that can enforce integrity or access controls, a policy that could periodically come in and verify that a desired property has actually been preserved over time. So these policies then are really how we characterize the consensus. And what we're observing is that the use of policies to define community interactions, originally we had in our data management middleware, but now it's migrating down into the storage controllers, and it's migrating up into the network. So we'll get some slides later on about groups that are integrating policy management with the existing internet. So this is software-defined networks. The software we build is the integrated rule-oriented data system. This is a second-generation data grid. You can take data that's distributed across any network-accessible device and organize it into what looks like a single logical collection. It's no longer sufficient to have a file system which just manages data. A file system will tell you, here's some bits, but it doesn't have any metadata about the bits. It doesn't have any real policies other than access control associated with the bits. So we think of data as the bits, the zeros and ones that are written somewhere. By themselves, the bits are used. And with this approach, we can build a system in which we can manage all three aspects and map what the community is trying to do to something that can be automated. So in this environment, we can build a distributed digital library, a data grid, and archive. So this is the way it works. There is a network. You have your preferred client that you're going to connect to the network with it. And the network connects to middleware. This is software that's installed on a server somewhere within the environment. So I have software that sits in front of storage resources, software that basically manages interactions with the database, software that manages interactions with a message queue, and software that manages interactions with schedules. All of these middleware servers could run on the same computer, or they can run on any computer somewhere in the world. So this is a distributed environment. It's called a peer-to-peer architecture because these servers can talk to each other. Our approach is based on this idea. In order to know what's the driving purpose for the collection and what are the properties that they want to have assigned to this collection they're assembling. So the top two lines are basically English natural language. Tell me what it is you want the system to do. When I run the procedure, I generate persistent state information, which I've got to manage and store. So if I make a replica, somewhere I have to store where the replica was put. And then I can write policies that go in and look at either the state information or audit trails or the actual data to verify that a required property was maintained. So I can do an end-to-end environment. I can specify what I want the system to do, and then I can check if the system actually do it. And then we federate these environments. So independent data grids can talk to each other and control how they want to interact. So you have interactions of the users with the collection and interactions between the collections that can be controlled. So we build a concept graph for the Research Data Alliance. So in this collection, we get to decide what's the arrangement of the digital objects, what attributes are associated with the objects, what attributes are associated with the collection. Typically, a group will define their required purpose and then come up with a set of properties they want their collection to have. So I want this to have integrity, authenticity, and have access controls. Each of those properties themselves have features. I want integrity to apply to all of the objects in the collection. I want to be able to verify that the integrity algorithm works correctly. I want it to represent my consensus of my community, etc. So given the desired property, we get to turn that into a policy. So if I want integrity, then I probably need to replicate the data. So if one copy goes bad, there's another good copy. I need to have a checksum so I can verify that yes, it hasn't been. So I could have, if I need a replication policy, then somewhere there needs to be a procedure that actually does the data object replication. So this policy, integrity policy would control the execution of the data object replication procedure when and where it's actually applied. I could apply it immediately when the data goes in. The data could go to a staging area and I could apply it within the staging area. I could control that you can apply to the operations. Every time an operation runs, it generates state information which then gets managed as an attribute on the data.
So if I replicated the data, then up there I've got a data replica number that now is an attribute on that file. I also had to store the location of the file, when it was created, a variety of pieces of information. To interact with this environment, we had to instrument the middleware with policy enforcement points. So you, with your favorite client, access the data grid. The data grid starts executing its software and it'll hit a policy enforcement point. At this place, it'll go off to an external rule base and ask what's the rule that should be applied. It will pick the correct rule to apply, execute it, save the state information, and then go on. So every action that we want to apply policies to have to be tracked by some policy enforcement point within the code. Finally, we can do periodic policies. So every week we can go in and verify integrity or verify where the data came from, etc. In practice, what happens is that there are these 5 major purposes that people have: archive, data grid collection, digital library, processing pipeline. When we distribute the software, we manage 7 default namespaces. So we manage attributes about users, about the files, about the collections, about the storage system, the rules, the microservices, and the metadata. So we can associate attributes with any of those namespaces. The system comes with 11 default policies related to distributed data management. So it's actually a very small number of policies you need to initiate a distributed data management system. Those policies control 11 default procedures, which use some of these 317 basic functions. So there are a large number of basic functions that are provided from which I can compose the procedure I need for a given policy. And from those 317 microservices, we generate 338 different state attributes related to one of these namespaces. Currently, there's 70 policy enforcement points and more than 50 clients coming in. So from a policy enforcement point, I might trap anything, actions that occur every time a file is put into the system, or an action every time I replicate a file, or an action every time I add metadata, but some type of action gets trapped, and then I can have a policy control what happens. So we slowly add policy enforcements over time. We add microservices, we add procedures, we add policies, we add metadata. So this is a highly extensible environment. You can add a new policy that controls a new basic operation, and then you can write a policy that migrates data from the old environment to the new. So I can continually modify what I'm managing in the system. The consensus of the community can change over time, and the system can track the change in the consensus. So within the DataNet Federation Consortium, we're trying to provide examples of managing not only data, but also information and knowledge. So I'm going to go through some very quick examples of knowledge management. How you actually characterize knowledge, trap it in procedures, apply it to data. Our goal is reproducible science, or data-driven reproducible research. If I generate a result, somebody else should be able to recreate my result by doing the same analysis. And can I capture the input, the analysis, and the output, share them so somebody else can verify my research? So when we capture knowledge, we're really characterizing that knowledge through the set of policies and procedures we want to run. We have 3 different types of knowledge we need to use right now. I need the knowledge for how to interact with your preferred data management environment. So your environment has a preferred protocol. So somewhere in my system, I've got to be able to capture the knowledge of how to interact with your protocol. We can encapsulate that knowledge in a microservice, one of these basic functions. So we can register into this distributed environment data from any external resource for which we have captured the required interaction protocol, which we do in a microservice. We also want to capture the knowledge related to analyses people perform upon the system. So someone might want to grab data from multiple sites, run a hydrology watershed computation, and they want to be able to register that computation, share it, so somebody else can get the same result back. But then we have the knowledge that we have within the data management environment itself. What are the policies and procedures we're going to use to manage the result? So 3 types of knowledge. How do I get to the data? How do I manipulate it? How do I manage the result?
And then do you have some sort of reporting procedures that, like, you can grab any piece of data and get a little report on what the pipeline has been on that piece of data?
Yes.
Good.
So here's an example. We're working with the Institute for the Environment at UNC, and they do hydrology analyses. And their challenge is that the data comes from the EPA, from NASA, from the U.S. Department of Agriculture, from the U.S. Department of Transportation, from USGS, from NOAA, climate records, from Kawasi precipitation records. So you've got all of this data in different agencies, and I need to grab the appropriate subset for the particular area I'm going to analyze, transform it into the required structures for my computation to work, and then automate that entire process. So typically, more than 80% of the effort is spent in the data acquisition, and 20% or less is actually in doing the analysis. And once the graduate student has done the analysis, the professor has no idea where they really got the data, what was really done to it. They got the result, but there's no way to go back and do it because all of the operations were done by hand. So we can write a microservice that actually accesses the data from the remote site using the remote sites protocol. We can write a microservice that transforms the data to the required structure. We can chain them together so that when you actually want to run your model, you just click on this workflow and the system goes out and does all the work. I can then share the workflow, share the input, share the output. So someone can re-execute my analysis, or they can change the input and see how their results compare with my results based upon what was changed. Or they can try to make certain that if they do the analysis on a new set of hardware systems, do I get the same result or did it change slightly? So this gives you a way to go in, register your workflow, associate automatically the input and output files with it, and then be able to share and reproduce the results. Another example is for the Oceanography Observatory Initiative. They're working with stream data. So I have sensor data from sensors out in the ocean, from ships, from satellites, and it's streaming in. And I need to be able to automatically archive a data stream. So traditionally, you take the data for some time period, aggregate it into a file, put the file in the archive. Now somebody comes in and says, I want the time series corresponding to day 1 to day 10. And then I would have to figure out how was the data stream partitioned into files, and then try to grab the correct files, extract the beginning set, the end set, because there are partial IOs on files, concatenate them together. So this approach allows you to have the system automatically do that. You can take a data stream that's being organized into discrete files, index each of the files so you know what time is applied for the start and end of the data in the file, and then you give the collection the time interval you want, and it does all the aggregation for you, all the partial I/O. So you can get back from the system the exact time series you wanted, even though the data has been chunked and stored separately, possibly in different sites. So this software currently is available open source at diceresearch.org or irods.diceresearch.org. We are working with the Renaissance Computing Institute to build a long-term sustainable version of this. So there's an iRods consortium, and we're making certain that the features we have available in our version are available in their version. So that's a version that'll be out next year. I said that policies are migrating into the network. So the future internet architecture has something called a software-defined network. They have a system called OpenFlow running in the routers, and I can talk to the OpenFlow system and change the routing instructions. So they have a way, based upon some policy for interacting with the router, to modify where you go to get data. This is important. If I want to get data very quickly and the file I'm going after has multiple replicas, I want to go to the closest replica and get the data from there. So either I have to do that externally to the network, have all the knowledge, but with this environment, could the network find the closest copy for me so I don't have to do the work? So what we're doing is we're integrating policy-based networks with policy-based data management. You could think of a virtual collection managed by the data grid interacting with the virtual network defined by the OpenFlow routers. So I can then, once I map those two together, be able to have the network optimize all the transfers for me. It also means I could start doing things like addressing data by name instead of IP address, because the network will be able to go to the data grid and find out where it was supposed to go. I'm able to do access controls in the network, so I can actually set up privacy in the network. I'm able to do debugging in the network. I can single step through the routing and see where the data packets really are going for a given request. So there are a variety of reasons why there's great interest in doing this. The people who try to move around terabyte-sized data files really need to understand where the data is moving and control the path. So there's a great deal of interest in this for communities that are doing massive data management. Another area is policies are now being thought about as an attribute you can put on the data itself. So instead of sending you a file with bits, zeros, and ones in it, I can send you a policy-encoded object. This is the object which is accompanied by the policies that control the interactions with the file and the rule engine that evaluates the policies. So I ship you this container. When you try to access the container checks, am I in an environment that I trust? If I'm not in an environment that I trust, then I'm not going to do anything. I say no. But it also allows me to specify what you're allowed to do with the data, even when it's been moved to somebody else's administrative domain. So this is a research area. We're working with the hierarchical data format group because they provide a standard container, and we can put our policies and rule engine in their container and then manage these interactions. And now my object has policies. It's now required that I have this software infrastructure installed.
But wait, are you saying that you can embed the policies in a way that you can have like access control built in
Yes.
to the container itself? So what ends up executing? Your system still has to execute the decoding or whatever.
So it requires some hardware extensions. I've got to be able to, within an operating system, have something that's embedded in the hardware, which is basically the checksum of that operating system. So is it a standard environment that I trust, or is it something that I haven't seen before?
Okay.
And then I have the rule engine that accompanies the software, so I just run my rule engine at the same time, and that reads the policies and decides what I can do. One last application. At SILS, we're supporting a student lifetime library. So the students get to decide on the type of collection they want to build. It's a personal digital library. And these are the different types of libraries that they put together. This is the interesting one because they're actually generating a reference collection they could then use in their professional career. And the SILS will maintain the digital library in perpetuity. Since it's the student's digital library, there are no requirements on the digital library itself. They get to decide the arrangement, how they're going to describe the material, what constraints they put on semantics or data formats, how they want to share it, what the access controls will be, how they're going to manage the ingestion and creation of the library itself. And typically the students who do this change their mind about each decision at least once during the semester. So it's a good pedagogy device. Here's why you really didn't want to do that. Here's something else you could have done that would make life easier. And since this allows you to change the policies and properties associated with your collection, they can do that. They can evolve their collection over time. It's not fixed in concrete. You made this decision, you can never change it. Instead, they're allowed to change. So they typically build collections from a couple of gigabytes to 100 gigabytes, 2,000 to 12,000 files, between 4 and 10 metadata attributes per item. The groups that do more metadata per item in larger collections have figured out how to automate ingestion, automate metadata extraction, because otherwise there's not enough time in a semester to do that. In the background, we have to provide standard management policies to ensure the integrity of the collection. So we have to, behind the back, replicate every file, manage checksums, periodically verify the checksums. We have to manage quotas. We turn on strict access control so only the students can see the content of their library. Replicate the metadata, even provide a way to reinstall the entire environment if we had a complete catastrophe. So there's a lot of management that goes on in the background to ensure that the assertion we make about the lifetime library will be preserved is possible. The students really worry about policies related to automatic synchronization of data from a laptop into the system or automated loading of metadata.
Wait, but so this, how much of it, when you say we have to provide for each of these projects that are using the system, how much are your team having to do setup and do management of it versus the people that are, you know, running the programs or something, setting it up themselves?
We set it up once and we're done.
Okay.
So for the same, as long as I'm going to apply the same policies across all the collections that are put into the system, it's easy. If I have a collection that comes in that requires completely unique properties, then I've got to set up the rules, procedures for that one. But the student digital libraries actually are running under uniform policy management or uniform management criteria. So we do this for every collection, and I only have to set it up once. So in practice, this from a prior class was the number of metadata attributes per file. So the ones that have more than 4 figured out how to automate metadata generation. The ones that have less than 4 had to do it by hand. So this is open source software. You can download it, install and run it. The EIRODS version is a binary release and it installs in 27 seconds. The version that we provide is a source distribution release, and it takes 30 minutes to install because we have to compile Postgres and ODBC from scratch, and that takes 27 minutes. So the software itself takes about 3 minutes to compile. So we're always interested in having more groups take advantage of the software, collaborations with broader environments, and so we welcome any questions about the software. Thank you.
Something I'm curious about is does it require the data to be a common language for all the members of that community? So when I look at astronomers versus archaeologists, they have a different language base that they use.
Yes.
How do they share that information?
So in this environment, we use schema indirection. So I can specify the attribute name, and I can add an arbitrary attribute to any object in the collection or any file. Or I could have a policy that all the files in this collection will have the same attributes, like Dublin Core. And so each community ends up specifying the different set of semantics they require for describing their data.
So they share within community. And
Yes.
This is the community deciding on policies, the community deciding how they're going to share the data. This isn't for, you know, if they're going to share outside of it, the community could be super wide, then they'll have to set up
Correct.
policies for which pieces can be shared with this
So
community and how would that be accessed.
I would take the information I'm assembling and then register it into one of these global information catalogs that somebody develops. The information catalogs just allow you to discover data. They don't do the data management. So we're doing the data management. We would register the data into somebody else's, like Data One's information catalog.
So I'm curious with, I mean, this is you know, I'm sure it's somewhat streamlined, but this is a fair amount of overhead to add to a collection. Do you have like guidelines that you give people when you're meeting with them, like how big their sharing network or how big their collection should be before it's worthwhile, or how much automation they would really need before it's worthwhile to set something up under this?
So we're dealing with data that's on a file system. So I have three latencies to worry about. One is there's a seek latency on the file system of 5 milliseconds. There's a spin rotational latency for a disk of 10 milliseconds. And then there's a internet-wide network latency, which could be 60 to 100 milliseconds. So when I interact with data in the distributed environment, I want to be faster than that 5 milliseconds.
Well, I'm thinking about like upfront, like setup, like this takes a reasonable amount of setup, I would assume. So like how big a project does something
Yes.
need to be? How widely do you have to be sharing, or how much automation has to be done before it's worthwhile to kind of set this up versus just having your own file system, having your unique database? And then I guess along with that, do you see people using this for really smaller collections just to add on this kind of provenance information and validation and all these sorts of things?
So I run everything on my laptop. Everything is sitting here. I have my own personal collection. I take it with me wherever I go. So we have collections that are a few gigabytes in size. One of the reasons the students were interested is they don't trust social media, so they want to harvest and maintain their own copy. If the social media site goes away, they're safe. So there's a driving purpose which justifies the effort. Any group that's trying to manage data distributed across multiple administrative domains, a data grid is the only solution. Otherwise, I have to replicate everything, but then how do I manage access controls? How do I put metadata on it? How do I do the arrangement? That's what the data grid does for them. Any group that's trying to enforce management policies now in a distributed environment, again, the data grid's the only software that does it. So you've got to have a driving purpose. If I'm happy putting 1,000 files on a file system, then I don't need the software. If I wanted to add metadata attributes, then I need something that will allow me to do it. So it really is driven by the purpose. So all of these people basically had projects that involved researchers across multiple institutions, and they needed to be able to collaborate on a shared namespace.
How much, so I come through the sciences also, and there's kind of it's not always done in an ideal way, but at least there's a built-in history of trying to do reproducible research, or that's at least the goal. How much do you see this starting out to be more of a conversation within the humanities as well? Because I see people mentioning off and on with digital humanities work. I get the feeling that that it's not necessarily as much a part of the publication ideals and stuff to do the kind of documenting of what your whole process was. I don't see as many like methods sections and stuff. Do you see this with your position? Do you see more discussion popping up amongst digital humanities in terms of the reproducible research?
We see that happening. An example is medieval manuscripts. There are 3 major institutions that house them. And so they're very interested in, can I federate all 3 environments together and now start looking at analyses that span what's at one institution. But it is cultural. If you're used to your research is independent and you do it entirely by yourself, then there's much less interest, incentive for a collaboration. So in the science and engineering domains, the research projects are so large you have to collaborate, and therefore you need a way to do it. If you defined a similar humanities project where people really needed to collaborate across institutions, then they would be interested in this. So if you can assemble the complete works of Faulkner here, then you don't need to go somewhere else. But if somebody else has part of the holdings, then you want some collaboration so you can look at their data too.
Produced by Duke University. Online at duke.edu.